All right. Hi, everybody. It is Miss Ducey talking to you virtually. I'm sorry I'm not here today. I'm actually in a training. If you have any reason that you need to talk to me urgently today before I'll see you on block day, I will be returning this afternoon, and you can always find me in my office or one of my classrooms. But happy Tuesday. Hope you had a really good long weekend. Today, our learning objective is that we're going to be talking about heat transfer instead of last week when we were talking about specific heat. So if you haven't already done so, your specific heat lab from last block day is due now at the beginning of the period. Hopefully that's already been collected, but this is just a second reminder, your specific heat lab is due. Now we're going to take a moment. You can take out your assignment sheet if you need to update any of these items. We got all the way up to item number 4 last week with our specific heat lab. Today, we're going to be going over our heat transfer notes. On block day, we're going to be going through a heat transfer lab. You will also be getting a heat test review guide because your test is upcoming this Friday. Another reminder is as you're filling out this assignment sheet, if any of these assignments are missing, it is your responsibility to turn them in by Friday for late credit because I will not be accepting any of these assignments after the unit is over. So I'm going to give you one more minute if you're taking down any notes for this assignment sheet for this week. I will also post it at the beginning of the day on block day. Okay, if anyone needs any more time, you could also ask your substitute to pause this video right here. Again, this is on my website and I'll also show this to you again next time I see you. So you should have this heat transfer note taker out in front of you right now. We're going to work through this and then you'll have a little bit of time at the end of class to work through the questions that I've given you at the end. So we're going to start with what is heat transfer? Well, it's the heat that's given off when an object's thermal energy is transferred. We've been talking about thermal energy being synonymous for our word for heat in this past week, but heat can be transferred from objects between 3 different ways, either conduction, convection, or radiation. So as you're paying attention and filling out your note sheet, we're going to be walking through these 3 different forms of heat transfer. So we'll start with conduction. You should be at the top of your note sheet here. For every single thing that we go through, you're filling out a definition as well as listing an example. So conduction is the transfer of thermal energy specifically through direct contact. By direct contact, I mean that objects must be physically touching one another in order for thermal energy to be transferred from one object to another. More specifically, conduction only happens when you're energizing molecules within a solid. So this makes sense. When you touch something that is hot, that has a lot of thermal energy, you have the potential to burn yourself. This is why when we've gone through our safety instructions in class, we've talked about how you should test if something is hot, like a hot plate, before you touch it. Metal actually conducts heat really easily, so when you make direct contact with it, thermal energy from a hot plate can be transferred to your hand through the process of conduction. Now, something specific that I've had you write down here is that conduction happens when molecules are moving, the energizing of molecules. We've been talking a lot in class lately about the movement of molecules. To remind you, when molecules are moving slowly, we're looking at low energy, cold temperatures. And when molecules are moving really quickly, we're talking about molecules that have high energy at hotter temperatures. Conduction specifically happens through collisions between neighboring molecules. So this is an example. If you were looking at sticking a glass rod into a fire, and if your hand is on one end of that rod and a fire is on the other end, what's going to happen is that as the solid is in contact with a lot of heat, the particles are going to start to vibrate as they gain thermal energy. Again, remember, more energy means more movement. As the particles are vibrating, they're colliding with their next door neighbor particles, which are going to start to pass along the energy. Eventually, that energy will reach your hand, and you will feel that thermal energy in the form of heat. Now, solids are really good at conducting because particles are closer together. Therefore, those particles are able to collide very easily. Only solids are able to do conduction. Conduction is not applicable to liquids or gas because those particles are really spread out, so it's very unlikely that collisions will happen. We also have some other examples of collision with conduction. So you can make direct contact with something that's cold, like your hand, to snow. That conduction, through that direct contact, you will feel a loss of thermal energy from your hand to the snow, which will be a loss of energy for you and will create a phase change in the snow of melting. We can also experience conduction through direct contact of warm things, such as holding your hand over a warm cup of tea. Thermal energy from the cup can be transferred to your hands where you will feel heat. Conduction is also the reason that you would want to wear insulated gloves when you're holding something hot, like a metal iron that you've stuck into a fire. The reason being, just like with the simulation you saw with the glass rod, is that as you're seeing these collisions between neighboring molecules, those molecules are going to transfer their thermal energy, and conduction will go up a metal rod to your bare hand. But we want to have protection between our hand, which can be easily burned, and a material that can conduct a lot of energy, like a metal rod. So you've written down your definition for conduction. You have an example for conduction, either sticking your hand in the snow, holding a warm cup of tea, holding a metal rod. But I actually want to skip down to the bottom of your notes here and explain the difference between a conductor and an insulator. Thermal conductors allow heat to flow very easily. So I've already given the example of metal. Metal is a thermal conductor. In that direct contact, as those collisions are happening through those particles, within a metal solid, they vibrate very easily, and are able to transfer thermal energy from one particle to another. This is how you cook food at home. All of the pans we use to cook food are all made out of metal, or we can also use glassware. Metal or glass, these solids conduct energy very easily. So when you put them over something hot, like an open flame, it will conduct that thermal energy so that you can heat up your food and cook some nice morning breakfast like eggs and bacon. There's also something called a thermal insulator. Insulators do not allow heat to flow very easily. We use insulators a lot here in Colorado to protect ourselves from the cold. We do not want our internal body heat easily conducting to the outside atmosphere when we're outside in the snow. So we wear puffy jackets, hats, gloves, which insulate us and do not allow our own body heat to easily flow to the outside environment. We're going to watch a short video which talks about a really amazing new technology of an insulator that has now been used to engineer new buildings in our world.
Nobel Prize-winning scientist Dan Kammen reveals the technology that could transform our cities and usher in a brighter future. This episode, buildings.
The energy demands of our buildings are simply unsustainable. If we can't find ways to make them cleaner, we commit ourselves to a warming future.
This is one of the strangest materials known to science. It helped a spacecraft survive a frozen hell on the surface of Mars. This man thinks it can transform our buildings and maybe transform the future of planet Earth. 2050. Ecopolis is booming. New buildings are rising everywhere, burning energy by the second. This demand for power pushes up greenhouse gases and pollution. 40% of a building's energy consumption is used for heating and cooling. But a staggering 1/3 of that simply disappears into thin air. Construction expert Don Young wants us to see our city's buildings through new eyes. He thinks if we could see energy as we waste it, we'd take action in a flash.
If people could see the world through these infrared eyes, the amount of sensitivity to these issues would skyrocket.
The yellow and red parts of the image show where most of the heat is escaping.
It's just phenomenal. I'm in this business, and I'm amazed at the amount of energy being emitted.
It shows there's a towering inferno raging through our cities.
I mean, these buildings look like they're on fire, really.
The problem is poor insulation. Buildings alone waste 13% of global energy production. That's equal to nearly 4 billion barrels of oil a year. We're building entire power stations just to heat up the sky. It's an unbelievable waste. But Don Young wants to reinvent our buildings. He's racing against rival companies to develop an astonishing material to keep heat exactly where we want it, on the inside. There is one place where extreme insulation is essential: the frozen wastes of space. And if this insulation can work in space, it might be the answer down here on Earth. Don Young discovered that NASA spent 2 decades investigating new kinds of insulation. They developed one of the most exotic and beautiful substances known to man. This astonishing material is called aerogel. Technically a solid, aerogel looks more like a trick of the light.
People refer to it as frozen smoke, and in some sense it is. It seems to be there just for the moment.
An incredible 99% of aerogel is nothing but air. It lets light through, but it won't conduct heat. This amazing property arises from its unique structure. Aerogel is made from a jelly-like substance, part liquid, part solid. The solids are fine chains of silica, surrounded by alcohol. To dry the gel, the alcohol is replaced with liquid CO2 under high pressure. As the pressure drops, the liquid CO2 becomes a gas. It bubbles away and leaves behind tiny air-filled pockets that are 1,000 times thinner than a spider's web. This elaborate honeycomb of air blocks heat instantly. In the 1990s, NASA put aerogel to the test in one of the most extreme environments in the solar system, the frozen landscape of Mars. On the red planet's surface, temperatures can plummet to minus 100 degrees Fahrenheit. Far too punishing for the sensitive equipment inside NASA's robotic probes. So NASA began encasing the electronics on Martian explorers in aerogel. If this advanced insulator failed, it would be a multi-million-dollar disaster. But aerogel delivered the goods. The Martian explorers beamed back stunning images and survived 3 frigid months. Don Young knows aerogel is the best insulator ever invented. But there are big problems with applying the space-age material in an urban environment. Aerogel is expensive and very, very fragile.
The main problem with the laboratory aerogel that had been around for quite some time is its fragility. It is easy to crush.
One squeeze, and aerogel explodes in a shower of dust.
It is easy to break and just very hard to imagine using it in any type of industrial setting.
Young's company spent 7 years making aerogel tough enough to use in buildings. Their solution is simple, but brilliant. The wet gel goes around a blanket of polyester fiber. This blanket provides a skeleton for the material, making it strong and surprisingly flexible. The finished product still has aerogel's incredible insulating properties, at a fraction of the cost of the material sent to the red planet. This is dry ice at minus 109 degrees Fahrenheit, as cold as the surface of Mars.
When I put my hand on this ice, I suffer almost immediate frostbite. Insulate that with 3 millimeters of our aerogel material. I can put my hand on this indefinitely for the day, if necessary.
If aerogel can block the cold, it should be just as efficient at keeping heat in. Young's betting his right arm on that. 3 millimeters, or 1/8 of an inch of aerogel blanket, stops a flame roaring at more than 3,000 degrees Fahrenheit.
We've been able to maintain all the magical properties, all the thermal properties that make the aerogel so important. Now we're in the midst of introducing the material into the building and construction industry.
Young's aerogel blanket is incredibly effective at insulating walls and roofs. But 30% of the heat lost from a building goes straight out of its windows. So Young is experimenting with see-through aerogel.
The holy grail of aerogel would be to one day be able to make an aerogel that could be transparent enough and strong enough to provide insulation within the window structure itself.
To plug the last gaps in our leaky buildings, Young believes we need aerogel window panes. So far, these high-tech windows are too fragile. Vibrations from a passing truck could be enough to shatter them. But Young is confident scientists will crack this problem. If they succeed, it could have a real impact on Ecopolis. The city's buildings kept hot or cool for a fraction of today's energy cost. Don Young is convinced that aerogel's glory days are coming.
think that we will have aerogel in every building. Aerogel will be as common in 2050 as materials like plastic are today.
Aerogel insulation, a very futuristic idea. But is it the best weapon for the war on carbon emissions? Top scientist Dan Kammen has the final say. He will decide if aerogel can crush Ecopolis's carbon footprint. The Center for Alternative Technology crunches the numbers, providing data for each technology's impact on Ecopolis's carbon footprint. This weird futuristic material scores an amazing 29% reduction in emissions. Maybe it could alter the future of Ecopolis.
So aerogel is a remarkable substance because someday it could help us engineer our buildings so we're not losing as much heat and we can actually be saving a lot of energy. So that's going to conclude conduction. So now on your note sheet, we're going to move on to our second form of heat transfer, which is convection. Convection is also a transfer of thermal energy, and it's the transfer through the movement of molecules, just like conduction, but instead of it being the movement of molecules through a solid, convection specifically transfers thermal energy within fluid moving particles, which would be the phase of matter of either a liquid or a gas. When a liquid or a gas becomes heated, our particles start to move faster and they become less dense. When I say less dense, what I mean is that as particles are heated up, they begin to expand. In order to explain how convection works, after you've written down this definition, we're going to move over to the right side of your note sheet and I'm going to go through a detailed explanation. Now, if you've ever been to the ocean, unfortunately in Colorado, this is not a sport that we are able to entertain, but the sport of surfing is highly dependent on the thermal energy transfer process of convection. So the question we want to ask ourselves is, why do surfers like to surf in the morning? On your note sheet, you'll see that I've left you a space to draw this picture and to take any notes as we explain this question. So, when you're at the ocean, the sea breeze and its counterpart, which is the land breeze, they're a regular local onshore versus offshore wind system. This wind system, onshore versus offshore, is experienced in warm climates where an ocean is present. This wind system is caused by the heating effect of the sun upon the land and the sea. For the wind pattern, the wind blows lightly offshore in the early morning before it turns onshore in the late morning. That wind then strengthens throughout the day before it calms down and gives a glassing effect to the water as we move into the evening. This wind pattern is very regular and very predictable for frequent surfers. This happens because the land and the sea are two different bodies. The land and the sea absorb the heat of the sun and they change temperature at different rates. Sea is made out of water land is made out of other materials. We already know that water has a very high specific heat, which means that water is going to have the ability to change temperature at a different rate than land. A solid, like land, heats up and cools down faster than a liquid, so in the warm summer months, the land heats up and cools down on a daily basis, whereas the sea temperature remains fairly stable, where it's rising slowly over the course of summer months. During a typical surfing day, the sun heats the land and causes temperature to increase so that the air above it warms and rises. Now, this is specific. Due to convection, hot air rises. This is due to that expanding effect. As we heat up particles, they want to expand outwards. Hot air wants to rise as high as possible. Once hot air is risen, this leaves space beneath it that must be filled. So the cooler air from above the sea is pulled in horizontally to replace that hot air. What this movement of hot air versus cool air does is it creates an onshore breeze. This is your local wind pattern. When you have a wind pattern, it's going to be pulling on the ocean waves to create waves that surfers would want to ride on. Without this calm pull of the warm air and cool air in the morning, we wouldn't have nice, safe waves for surfers to ride on. Throughout the day, as our wind patterns change, it changes the quality of the waves and makes it not as safe for surfers to surf on the waves throughout the rest of the afternoon and evening. Other examples of conduction, which again is the movement of thermal energy through a liquid or a gas, have to do a lot with our geology or fun everyday items. For example, a mid-ocean ridge, it's an underwater mountain range that's formed by plate tectonics. What happens is you have an uplifting of the ocean floor, which occurs when convection currents rise in our mantle between the oceanic crust, and they create magma where two tectonic plates can meet. You can also see the process of convection if you've ever owned an amazing household item called a lava lamp. Now, I don't know if lava lamps are existent a lot in your homes, but when I was a kid, having a lava lamp was one of the coolest things you could have. Lava lamps work on the premises of convection, where you're creating a current that can transfer heat from one liquid to another, which causes a motion of fluid through a current. We can also visually see a convection current occur. So this is an experiment where someone has used a small fish tank filled with water and placed it over one bowl of hot water and one bowl of ice. What you can clearly see as they've put in colored dye is that the convection current moves the water around in a circular motion. The convection current is transferring heat from one place to another by mass motion of a fluid, in this case, water. This can also happen in gases. This leads us to our third form of heat transfer, called radiation. Radiation transfers thermal energy through electromagnetic waves. Now, we've learned about electromagnetic waves before, but just to give you a reminder, these are things such as X-rays, which you might get to look at your bones or your teeth at a doctor's office. Electromagnetic waves come in the form of visible light, which we can see coming off of light bulbs. This can also come in the form of ultraviolet waves or infrared. Now, we just have finished a unit on matter, but what's amazing about radiation is that matter is not required for the transfer of energy to occur, because electromagnetic radiation occurs in the form of waves. All objects, including you and myself, emit radiant energy. So what humans do is we give off infrared radiation. Now, a lot of this radiation, it is not visible to the naked eye. We usually feel radiation in the form of heat. So in the video that you just watched, one of our engineers was using an infrared camera. What he was able to do was look at the electromagnetic waves of the buildings around him to see how much heat was being lost through structures like windows, drywall, and brick walls. Those infrared waves can tell us how much heat is being lost by an object. In the past, I've also given you the example of infrared goggles being used at night. What you can do is look through these goggles to see if another living object, like a human, which produces a lot of radiant energy, is present near you, even though you can't see it through the darkness. If you're looking forward to summer and laying out and sunbathing, you're actually going to be experiencing a lot of radiation. The sun emits ultraviolet rays. We can protect ourselves from these rays so we don't get a sunburn by using sunscreen. But ultraviolet rays come from the sun and can be moved through waves, through the space, through our atmosphere, onto the surface of the earth. This is a picture from NOAA, actually here in Boulder, looking at the sun. What this is showing us is that the sun is really hot, and the sun can produce enough thermal radiation that it can actually be transmitted through visible light. This is why during the day, our world is lit up and we can see each other. This is an example of looking through something like an infrared camera. On the right, you can see a scale of temperature dependent on the color that you're seeing through the camera. So this is a person holding a lizard. You can see that the person's hand is at a higher temperature, has more thermal energy than a lizard. If you know anything about lizards or reptiles, you do know that they're cold-blooded and that their bodies run at a lower body temperature. You can also use infrared cameras to look at the infrared radiation of our homes. You can clearly see that looking at the average household, that most heat is lost through windows, and you can also see at the top of the house, a lot of heat is being lost through an open area like a chimney. Now, it's really expensive to be running your heat on full blast all throughout the winter, so this is also why we cover our windows with things like curtains, and we might close up our chimneys when they're not being used so that we can minimize the amount of energy that's being lost as we're paying for our heat. So this concludes our lecture on our forms of heat transfer. So at this point, you should have completed this table. You should have information about conduction, convection, and radiation. In order to solidify our learning for today, we're going to look at one more video that in review is going to go through these three forms of heat transfer.
Transfer. What we're really talking about here is how energy moves, specifically heat energy, and how it gets from point A to point B, whether it be here on the surface of the Earth, up in the atmosphere, or even out in space. Heat transfer occurs really in three ways, and these include conduction, convection, and radiation. Let's take a look at each of these, starting with conduction. This is heat transfer as a result of molecular contact. The best way to understand conduction is by thinking about an example. So here I have a metallic spoon, and I imagine holding a match underneath it. Now what we know is that that spoon is going to heat up, and not just the part of the spoon that's over the match, but rather the spoon as a whole. And the reason this happens is because of conduction. Energy from the flame is causing the molecules within the spoon to vibrate, and that's transferring energy from one to the next, to the next, to the next, until the entire spoon has warmed up. That heat has transferred throughout the entire material. Conduction is going to happen most effectively in solid materials. But let's not forget about convection and radiation. Let's look at convection. This is heat transfer through or as a result of density differences. Again, let's grab that match and let's think about this for a minute. I think we all know it's probably not the best idea to hold your hand above an open flame like this, and that's because a lot of the heat energy generated by that flame is going to rise. That is purely because of the process of convection. You see, what's happening is the flame is causing the air to expand. And when it expands, it becomes less dense than the surrounding air and therefore floats upwards. And with it goes some of that heat energy. That's what convection is all about. And this is going to occur most effectively within liquids and gases. Finally, let's think about radiation. Radiation is heat transfer by wave motion. Let's pull that flame up one more time. I think we know that because of convection, heat is going to rise, but it's also going to travel outwards in the form of waves of energy, electromagnetic waves. And that's the third type of heat transfer. Radiation is really interesting in that it doesn't need a material for it to travel. So this can occur out in open, empty space. In fact, this is how energy travels from Earth's sun to the surface of the Earth. And so if we look back, we have our three types of heat transfer: conduction, convection, and radiation. And it's important to know the key word that goes with each one. For convection, it's going to be density differences. For conduction, it's going to be contact. And for radiation, it's going to be waves. We can sum all three types of heat transfer up in one diagram by looking at something as simple as a campfire. Imagine that you're camping and you hold a pot of water or stew above that flame. Well, right now in this one picture, we are seeing all three types of heat transfer take place. There's conduction happening as the flame is transferring energy directly to and throughout the pot as a result of molecular contact. Additionally, there's convection as heat from both the boiling pot and the flame itself is rising up as a result of density differences. And finally, there's radiation occurring all around the campfire as energy travels away from the flame in the form of electromagnetic waves. And that's a quick look at heat transfer.
All right, so hopefully in review, you have a solid understanding of our three forms of heat transfer: conduction, convection, and radiation. Now, for the rest of class, what you're responsible for is answering the following questions, starting here on your note sheet, working back through section 2 here, answering questions about figure A, B, C, and D, and then finally answering some matching questions provided from this word bank. All of the answers to these questions should be available to you from the notes that you have just taken. Now, you may work with a partner at a lab table, but do know that you're responsible for working through these questions, and if you do not finish them, you're going to have to be finishing them at home. I will be checking these for a homework grade when I see you at the beginning of class on block day. If you have any questions, you could ask your substitute to rewind the video to any place. This video is also posted on my website if you would like to review this at any point at home. Thank you so much for listening, everybody, and I will see you on block day.